Hi, my name is Gracie, and this is my presentation for Physics 2 Lab 3. The purpose of this lab is understanding the properties of magnetic fields using a magnetometer and utilizing the Biot-Savart law. And we're going to create a computational model of the magnetic field of the bar magnet with our experimental calculations. So some fundamentals we're using here is the Biot-Savart law, and specifically this derivative of it, because we're looking at B on the axis, like along the axis. And then this is a distance dependence of a magnetic field, and then we're going to utilize the logarithmic form of that, which you'll see later. And a brief review of the results. Mu from our experimental model ended up being 1.41 amps meters squared, and then B at 45 degrees in our experimental model was 5.41 10 to the negative 5 compared to the computational model being 1.83 to the negative 5. So the system would be the bar magnet and the magnetometer, and the surroundings would be everything else. And our initial conditions, we're setting it up so that we get a precise location of the magnetometer on the app that we downloaded. There were 3 apps on the lab sheet that you could have downloaded, but in order to find where it is, you're going to slide the phone across a ruler until you find exactly where the most accurate reading is, and compare to the magnet, and then you're going to do the same thing moving it up and down. So you're doing this until you find the strongest X and Y components. So for our experimental design continued, we collected data just moving the phone along different distances until it reached the B that was targeted. So for R20, we're finding the distance along the x-axis that gets us as close to this component of the magnetic field as possible. And so we're going to do that for all of these values, and we're going to do that 3 times to get an average. And then the Excel sheet from the lab sheet automatically finds a natural log of these and then graphs them. And the reason that we're taking the natural log is because when you do that and you plug it in, it gives you this equation, which is very similar to a linear equation. And using the linear equation, we can infer that n is going to be the slope, and then the natural log of k is the y-intercept. So using that, we can go to this calculation where you can find k by doing it the reverse of the natural log, putting it in e, and then n, we just did approximately -3. And then you can use that to find mu by rearranging this equation. Like I said, we're using this one because it's along the axis, and that got us to a final value of 1.4 amps meters squared. And then for part 3 of the experimental design, we're just recording the X, Y, and Z components of the magnetometer at a distance d. So first we slid it along the x-axis until B was 100, and then we lifted that to the same, we just matched the y to the found x component, and then that gave us this value of d. And then we have to make sure we're subtracting the y component of the Earth from the measured y component so that it's more accurate. And this was our final value we got. And for the coding, we're just trying to replicate a model of a magnetic field. And the way we did this was we took the starter code and we put our mu 1.4 into the code, and then we just did different observation axes, and then we went on to model some arrows that are going to act as models of the direction of the magnetic field. And so some assumptions that we're going to use going into the coding is we're ignoring the interference of nearby other electrical fields, like there was a lamp near my desk. We're ignoring the potential electric field or magnetic field that could have. And then we're assuming that the accuracy of the magnetometer and the experimental calculations that informed the code were correct. And so this is just the coding continued. This is us just essentially making arrows, and then we're going to make the 45-degree angles as well, and that's the value that we're most looking after because that's what we're comparing to our experimental data. So this D perp was taken from the average D perp from the Excel sheet. And the results, as you can see, the model pretty nicely kind of shows what a magnetic field of a dipole looks like with the arrows. Sorry, that's a typo. This is the experimental model, not the computational model. The computational model returned a value of 1.83 10 to the -5, but our experimental model returned a value of 5.41 10 to the -5, which is a significant difference, but we will get into that. So there was a significant difference between the computational model and the experimental calculations. I would say, though, that our experimental model was likely accurate. It was getting real-time readings of the magnetic field, but it's just not really possible to completely isolate the source of magnetic energy to just the magnet because we're constantly surrounded by different magnetic forces. So some potential sources of error would be exactly that there are other objects in the surroundings that are going to influence the reading that our phone gets, as well as we don't know exact coordinates of the magnetometer. We're just kind of making our best guess based on the magnetic readings. So the answer to my what if question is that the results of the X component would have been altered because it's being influenced by Earth's north-south magnetic field if we didn't account for that during our setup. And then another what if question is if there were two magnets, I would expect the magnetic field readings to double in value. Thank you.